All right, guys. In this video, we're going to be going over atoms and ions, basically. So the subatomic particles that make up an atom, and how does an atom become an ion, basically. Okay, and so what's the difference between those two things? What an atom specifically is, and also kind of how do we represent a particular atom or ion? What type of notation do we use? What do the numbers mean? Okay, so that's what we're getting into today. So let's go through this. I'm going to bring myself down here. It'll make more sense. Okay, so let's go through this outline and just kind of go through all the different things you need to know for 2-1, atoms and ions. Okay, so we're going to drop a few hints or a few details to 2-2, which is really getting into isotopes, but really what is the difference between mass number and average atomic mass. So average atomic mass is the mass that's on the periodic table. How is that different from mass number? So today we're going to focus on mass number, and then when we get to 2-2, we're going to be talking about how we actually calculate the atomic mass, or the average atomic mass, which is the mass that's on the periodic table. Okay. So first off, let's just jump into it. What is an atom? An atom is a type of particle. So when we were doing our mole calculations back in Unit 1, when you were going from moles to particles, one type of particle is an atom. So what is an atom a particle of? It's a particle of an element. So when you're looking at your periodic table of elements, all those things are elements. Carbon's an element, iron's an element, oxygen's an element, neon's an element, right? If it's on the periodic table, it's an element. Water is not an element. Water is a compound. It's a combination of multiple elements or multiple atoms. Okay, so if we have an element, the smallest unit of that element that still is classified as that element is called an atom. Okay, so if I have a sample of carbon, the smallest unit of that sample that still represents the element carbon would be called an atom of carbon. Okay. So understand there are smaller particles than atoms, and we're going to get into that right here in a second. We call them subatomic, below the atom level, or smaller than an atom. Okay, but and those are the particles that make an atom, but the individual particles that make an element are the atoms. Okay, so the smallest unit of a carbon atom, or of carbon, the element, is a carbon atom. Okay, so what's an ion? An ion is a charged particle. So one thing to understand are atoms are electrically neutral. So they don't have an overall positive or negative charge. But ions have to have either a positive charge or a negative charge. Okay, so we can classify ions two different ways. There's cation, and it's not cation, it's cation, and then there's anion. Okay, cations are positive. So if you have a positively charged ion, it doesn't matter if it's 1 plus or 2 plus or 3 plus or 4 plus. If the charge is positive, that's called a cation. If the charge is negative, -1, -2, -3, it's usually, when we say charge, it would be 1 minus, 2 minus, 3 minus. If the charge is negative, that would be called an anion. So cations are positive, because I guess cats have paws, or cats are good. And then onions, but really anions are, they smell bad. I don't know, they make you cry. Maybe that's a way to remember a cation versus an anion. Cations positively charged, anions negatively charged. Atoms, neutral, no charge. Okay. So atoms are made up of subatomic particles. Okay. There's 3 main subatomic particles that make up an atom, but then 2 of those subatomic particles are made up of even smaller subatomic particles. And you gotta know the name of those really small subatomic particles, but you really don't need to know much more about those. Okay, so the 3 main ones that we're going to focus on are protons, neutrons, and electrons. So if I ask you what are the subatomic particles, this is really what I'm looking at for, protons, neutrons, and electrons. But it's also good to note that there are some things called quarks, and quarks are what make up protons and neutrons. So you can break down an atom into smaller particles. Those smaller particles are protons, neutrons, and electrons. But then you can break down protons and neutrons into even smaller particles called quarks. Okay, that's really all you need to know about quarks. But you know, if protons and neutrons are in the nucleus, that technically means quarks are in the nucleus, because quarks are what make up protons and neutrons. Okay, so just kind of a vocab word to be aware of. It's a subatomic particle. They're what make up protons and neutrons, but that's basically it. Okay, the three main ones are protons, neutrons, and electrons. Right. The reason why we put them, I put them in that order, is because the protons and the neutrons are in the nucleus. So if this is an atom, the center of that atom, think of it as a sphere. The center of that sphere is called the nucleus, and that's where the protons and the neutrons are. And then what's on the outside, in what we call the electron cloud, sometimes known as orbitals, but that gets a little funny. We'll talk about what an orbital actually is when we get to Unit 3. But right now, just, you know, protons and neutrons inside the nucleus are the nucleus in the center of the atom, and the rest of the atom is the electron cloud. So the electrons are on the outside, protons and neutrons on the inside. Basically, that's the way to think about it. Okay. This picture is not at all representative of the size of the nucleus compared to the size of the electron cloud. The nucleus is way, 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 way small compared to the size of the cloud. So if we wanted to make this more accurate, we would put just a single dot on the screen that would represent the nucleus, and then the rest of the screen would be the electron cloud. And if you really want to put it in perspective, if the nucleus were the size of a marble and you put it on the 50-yard line of like a big football stadium, the rest of the atom would be the size of the football stadium. Not just the field, but the entire stadium. So like, that's how small the nucleus is. So when we draw it, we don't draw it nearly to scale. So just, you know, understand that, okay? So what do you need to know about protons? They're in the nucleus, and they have a charge of 1 plus. So each proton is 1 plus. So if you have 2 protons, that would be 2 plus. If you have 3 protons, that would be 3 plus. And they have a mass of 1 AMU. Now, AMU, I'll type it out here, stands for atomic mass unit. Okay, so each proton has the mass of 1. 1 what? Not 1 gram. That's too big of a mass for a single proton. It's 1 atomic mass unit. Okay, and if you want to put that in perspective, I have it down here. 1 AMU is equal to 1.7 essentially times 10 to the negative 24 grams. So take a gram, you know, multiply it by 10 to the, or divide it by 10 24 times, and that's what an atomic mass unit is. Okay, so just kind of understand, AMU is a really small unit of mass, but we're talking about the mass of a single proton. Okay, so neutrons also in the nucleus, but they have 0 charge. They're neutral. That's why they're called neutrons, neutral. But they also have the same mass as a proton. Okay. Now, technically, neutrons are slightly more massive than protons, just a tad. But we'll just say 1 AMU for neutrons, 1 AMU for protons. Okay. And then what you need to know about electrons, they're outside the nucleus. Okay. Or in the electron cloud. We're going to actually give structure to the electron cloud when we get to Unit 3. Okay. But right now, just say they're on the outside. Right? The valence electrons are the ones that are furthest out, right? And then you have the rest of the electrons, but the electrons are in the electron cloud, and in the center of that cloud, and again, you got to think in terms of a sphere, not a circle, but 3 dimensions of space. Inside the center of that sphere, very small thing, that's where all the protons and the neutrons are, okay? So they have a charge of -1. So their charge is the opposite charge of a proton, okay? So a proton is 1 plus, 1 electron is 1 minus. 2 electrons would be 2 minus, 3 electrons would be 3 minus, and so on. Okay. All right. But here's the deal. Electrons don't have mass. Okay. Now, they technically have a little bit of mass, but the mass of an electron is such a small fraction of the mass of a proton and a neutron that we'll just call the mass of an electron 0, okay? So if you want to know the mass of an atom, all you really care about is the protons and the neutrons. If you care about the charge of an ion, then you have to worry about protons and electrons. So charge, your focus should be the protons and the electrons. Mass, your focus should be protons and neutrons, because electrons don't have mass, okay? So here's kind of a little chart, memorize it. That's kind of what we need to know right now, okay? We're gonna give a better understanding or get a better understanding of the structure and really focus on the electron structure, so the electron cloud structure of an atom when we get to unit 3. Right now, just protons, neutrons, nucleus, electrons outside, okay? So, now, if I have an atom, how do I know how many protons, neutrons, and electrons does it have, okay? So a couple things we gotta know, right? So on our periodic table, we're given 2 numbers. One of those numbers is called the atomic number. Atomic number is equal to number of protons. And if you see capital Z in an equation anywhere that involves chemistry, that is the atomic number. Z represents the number of protons, which is the atomic number, okay? You can always find this on your periodic table. You always have access to your periodic table, okay? So here's an example. If I look up on a periodic table, this is what I get for carbon. This is the chemical symbol. Our periodic tables actually have the chemical name as well, so it would have the word carbon here. Okay, this one didn't, that's okay. But notice we have 2 numbers. This number is called the atomic number, so this would be the number of protons, okay? And this number is, right, remember we were learning that number in unit 1 as what we called the molar mass. Now we're gonna talk about it as the atomic mass, okay? But understand, this number is called the atomic mass, which is short for average atomic mass. Sometimes it's called atomic weight, depending on what periodic table you're using. It's the same thing. What it's not the mass number. So we're gonna talk about something called a mass number here in a second. That is not the number that's on the periodic table. The number that's on the periodic table, the 2 numbers, one of them is the atomic number, and that's always the smaller whole number. That's the atomic number. And then this number is called the mass number, or not the mass, well, it's called the average atomic mass. It's not the mass number, okay? And so remember, this number, last unit, we were referring to it as the molar mass, and the units for it would be grams per mole when you're referring to it as the molar mass. But these units, if you're talking about the average atomic mass, it would be AMU, atomic mass units, okay? All right, so atomic number is the number of protons, and that's what identifies the element. So the number of protons an atom has tells you what element it is. So if I look at a nucleus and I see that it has 7 protons, then I could go to my periodic table, find atomic number 7, which is nitrogen, and I know that's an atom of nitrogen. So any nucleus that has 6 protons would be labeled a carbon atom, or a carbon ion if it was charged. But if it was neutral, if you have 6 protons in the nucleus, that's a carbon atom, right? So you just go to your periodic table. Here, let me scroll down. I got a periodic table. Where do I have it? Right here, right? So any oxygen atom has to have 8 protons. Any fluorine atom has to have 9 protons. Any neon atom has to have 10 protons. If you change the number of protons, you change what element it is, right? If I have 11 protons and then I go to 10 protons, I've changed my element from sodium to neon. Okay, so number of protons is atomic number is number of protons. It's what identifies the element, okay? All right, so let's go back up. All right, okay. So, mass number is equal to how many protons an atom has plus how many neutrons an atom has. So atomic number plus number of neutrons. So you can change this equation to A is the symbol for mass number equals Z plus N, where remember Z is the atomic number, which means number of protons, and plus N would mean the number of neutrons. Okay. So how do you get the mass number? You have to take the atomic number and add the number of neutrons you have, and that's going to be the mass number of the atom. Okay. So understand, when you're given an atom and you're asked how many protons, neutrons, and electrons, you're probably going to be given the mass number of that atom. So if you're given the mass number, you always know the number of protons because you can look it up on your periodic table. That's the atomic number. Mass number minus protons would give you neutrons. So you're either going to be given the number of neutrons so you can add it to protons to calculate mass number, or you'll be given the mass number so you can subtract the protons from it to get the number of neutrons. Okay? So, number of neutrons can change, right? And what would that do? It would change the mass of the atom. So isotopes are atoms of the same element with a different mass number. Now, remember, if they're atoms of the same element, that must mean their atomic number is the same. They have to have the same Z number, the atomic number. So the only way you could be atoms of the same element with a different mass number is by having a different number of neutrons. So here's the example of the isotopes of oxygen. Here are 3 isotopes of oxygen. You have oxygen 16, you have oxygen 17, and you have oxygen 18, right? When we go to the periodic table, the average atomic mass of oxygen is 16. But that doesn't mean all oxygen atoms have a mass of 16. Most of them have a mass of 16, but there's some oxygens with a mass of 17, and there's some oxygens with a mass of 18, okay? What's the difference? The number of neutrons, right? If it's oxygen, it has to have 8 protons. So oxygen 16 has 8 protons and then 8 neutrons, because 8 plus 8 is 16. Oxygen 17 has 8 protons and 9 neutrons. 8 plus 9 is 17. Oxygen 18 has 8 protons. Again, it's oxygen, so it has to have 8 protons. So the only difference is the number of neutrons to get that different mass number, okay? So this is the name notation for isotopes, and this is the symbol notation for isotopes. So when we are given an isotope, they're either going to say the name and the mass number, or they're going to give you the chemical symbol with the mass number on top. Remember, that gets the symbol A, and the atomic number on bottom, which is the symbol Z. All right. So here are the isotopes of carbon in name notation, and here are the isotopes of carbon in symbol notation, basically. Okay. So carbon has 3 isotopes: carbon 12, carbon 13, carbon 14. All right. Well, since they're carbon, and you go to the periodic table, the atomic number for carbon is 6. So each of these isotopes have to have 6 protons. So what's going to be the difference, right? As I go from here, this is 6 protons, 6 neutrons. This is 6 protons, 7 neutrons. This is 6 protons, 8 neutrons. Okay. All right. So again, given mass number, you can find the number of neutrons by subtracting the atomic number of protons. Okay. Given number of neutrons, you can find the mass number by adding the number of protons, the atomic number. Okay. So what about the number of electrons, right? So, we can find the number of protons and the number of neutrons, right? Number of protons, we look up the atomic number on the periodic table. Number of neutrons, we subtract the mass number that was given to us from, or the atomic number from the mass number to get the number of neutrons. But how do we find the number of electrons? Okay. Well, remember, if we're talking about atoms, they're electrically neutral. Okay. So what does that mean? It means you have the same number of protons and the same number of electrons. So if you're looking at an atom which isn't charged, it doesn't have a negative charge or a positive charge, if you're looking at an atom, then the atomic number is also the number of electrons. So atomic number technically is number of protons, but because atoms are neutral, number of protons has to equal the number of electrons or vice versa. They cancel each other out. So for every positive 1 charge I have in the nucleus, I have to have a negative 1 charge in the cloud to balance it out to have an overall charge of 0. Okay? It has nothing to do with the neutrons because neutrons are neutral. Okay? All right. So here is isotope of uranium. This would be uranium-235. So let's understand. This is the chemical symbol. this number is the mass number of this particular isotope of uranium, and this number is the atomic number, okay? So all I have to do for protons is to say the atomic number, which was 92, all right? So protons, this atom has 92. Now, there was no charge, so that means it's an atom, so that means also 92 electrons. If I have 92 protons, I gotta have 92 electrons to be neutral. But how do we get to the number of neutrons? We'll do mass number, which was 235, we'll subtract 92 from it, and what's left over is the neutrons. Okay, so this isotope of uranium has 92 protons, it has 143 neutrons, and because it's neutral, it would also have to have 92 electrons. Okay. But here we had gold. They gave us an isotope of gold, gold 198, all right? But, so in this type of notation, they don't give us the atomic number. Well, don't worry, you always get your periodic table, so go look it up on the periodic table, okay? So we find gold on the periodic table, its atomic number is 79. So I know I got 79 protons, it's neutral, so I got 79 electrons. And then again, I'm gonna do neutrons, I'm gonna do 198 minus 79. I don't care about this number, okay? So this is the average atomic mass of gold, but I don't care about this number right now because I'm not looking at the average of gold. I'm looking at a particular gold atom that has this mass number, okay? So I'm not worried that the 198 doesn't match this mass on the periodic table because I know they're different things. This is telling me the mass of a particular atom I'm looking at right now. And this is a weighted average of all the different types of gold atoms there are. Okay, and we're going to learn about how to calculate that in the next part of this unit when we get to 2-2. But right now, I just care that it's gold with a mass of 198. So 198 minus 79 will give me my number of neutrons. Okay. So again, 79 for protons and electrons because it was neutral. I know 79 protons because that's the atomic number. And then 198 minus 79 will give me that number of neutrons. Okay. All right. So ions, all right, how do they form? Okay, well, remember, protons identify the thing. So if I have 8 protons, I'm oxygen. If I have 11 protons, I'm sodium. If I have 3 protons, I'm lithium, right? So atoms that turn into ions can't gain or lose protons to get a charge. So what they have to do is gain or lose electrons to get a charge, because you can't change the number of protons. Changing the number of protons changes the identity of the atom, okay? So how do ions form? You either gain electrons or you lose electrons, okay? Okay, again, you cannot gain or lose protons. Changing the number of protons, changing the atomic number, changes what you're looking at, okay? So how to become a cation? Well, this is where we got to think about it. Remember, electrons are negative. So if I gain electrons, I'm going to become negatively charged. If I lose electrons, then I'm going to have more protons than electrons, and now I'm going to be positively charged. So to become a positive ion, which is a cation, if I want to become a positive ion, I got to lose electrons. Every electron I lose, I gain a positive charge. So if I lose 1 electron, my charge is 1 plus. If I lose 2 electrons, my charge is 2 plus. If I lose 3 electrons, my charge is 3 plus, okay? But to get a positive charge, I lose electrons, okay? To become an anion, a negative ion, you have to gain electrons. And every electron you gain gives you another negative charge. So if I gain 1 electron, I'm 1 minus. But if I gain 2 electrons, I'm 2 minus. If I gain 3 electrons, I'm 3 minus, and so on, okay? Right? We're neutral when the number of protons and electrons are equal. If the protons is greater than electrons, I'm going to be overall positively charged. If the electrons are greater than protons, I'm going to be overall negatively charged. Okay, because electrons are negative and protons are positive. Okay. So here's a question. Now, instead of finding protons and neutrons and electrons in an atom, now we're trying to find protons, neutrons, and electrons in an ion. Okay. Well, for neutrons, it's not going to change anything. Okay. It's still mass number minus protons. Okay, so to find the neutrons in this thing, I would do 17 minus 8, right? So I know I have 9 neutrons, okay? Protons has to be the atomic number, so I know I have 8 protons. But now I have a charge, okay? So because it has a charge of 2 minus, I have to understand what that means. A -2 or a 2 minus means you've gained 2 electrons, okay? So what we have to understand is, if it was neutral, you'd have 8 protons, 8 electrons. The -2 means I've gained 2 more. So you know that you originally, oxygen starts with 8 electrons. A -2 means I gained 2 more. So this ion has 10 electrons. 8, as it started out as a neutral atom, and then to get to a -2, I had to gain 2 electrons. Okay? So in this ion, the oxide ion here shown, I'd have 8 protons, I'd have 10 electrons because my charge is -2. And how did I get the 9 neutrons? The mass number, which was 17 in this case, -8. If this had been 16, if this mass number had been 16, then this would be 8 neutrons, okay? But it wasn't, it was 17. So this particular ion of oxygen has a mass of 17. Well, how did it get there? Well, it only has 8 protons, so it has 9 neutrons to get to that mass, okay? Let's do one for a sodium ion. Now, a sodium ion has a charge of 1 plus, okay? So 1 plus means I've lost that many electrons. So in this case, I've lost 1 electron, okay? So protons has to be 11. That's what this number represents. 1 plus means I lost an electron, so I went from 11 electrons to 10 electrons. Okay, so I have 11 protons, but I only have 10 electrons. That's why the charge is 1 plus. And then to get to the number of neutrons, I would take that mass number 22, subtract 11, and in this case, I have 11 neutrons as well. Okay. Let's do it for another ion. In this case, a nitrogen ion or a nitride ion. Okay. Notice its charge is 3 minus. That means I gained 3 electrons. So start out with 7 protons, always 7 protons. Okay, that's not going to change. But I normally start, nitrogen would have 7 protons and 7 electrons, but the 3 minus means I gained 3 more electrons. So now 7 plus 3, I have 10 total electrons. And then again, I got the 7 neutrons by doing the mass number, 14 in this case, minus the atomic number 7 in this case, to get the number of neutrons. Okay, so this ion has 7 protons, 10 electrons, 7 neutrons. Okay. All right, now let's look at this one. Okay, this one, we got a magnesium ion. Notice it's a 2 plus. So 2 plus means I lost 2 electrons. Okay, so we know that the the protons would be 12, which is the atomic number. The neutrons would be mass number minus 12, so 25 minus 12. That's how I got 13 neutrons. And then again, 10 electrons. Okay, right here, because I started with 12, and the 2 plus means I lost 2, so I have 10 electrons. Okay. Now, hopefully you noticed something as we were going through this example. The oxygen and nitrogen ions had 10 electrons. The sodium and magnesium ions also had 10 electrons. Let's look at a periodic table and find where they are. Okay. So nitrogen and oxygen are right next to each other, and when they became ions, they got 10 electrons. Sodium and magnesium are right next to each other, and when they got ions, when they became ions, they each got 10 electrons. Okay. So what we're going to learn as we go through chemistry is this thing called the octet rule. And the way to think of the octet rule right now is atoms gain, lose, or share, and right now we're going to focus on gaining or losing because we're becoming ions. Atoms gain or lose electrons to get a more stable number of electrons. But right now, we're going to narrow that definition down and say to get the same number of electrons as their closest noble gas, okay? So this column right here, the last column on the periodic table, these are called the noble gases, okay? Notice neon has an atomic number of 10. That means neon has 10 protons, but it would also have 10 electrons, okay? Notice that oxygen, when it became an ion, had 10 electrons. Notice that nitrogen, when it became an ion, had 10 electrons. Notice that sodium, when it became an ion, had 10 electrons. Magnesium, when it became an ion, had 10 electrons. Okay? So what's nitrogen's closest noble gas? Neon. So when nitrogen becomes an ion, it's got to gain 3 electrons to get there. But when oxygen becomes an ion, it only needs to gain 2. So what do you think fluoride's going to be? Fluorine, the fluoride ion, is just going to be -1 because it only has to gain 1 to get there. Sodium only has to lose 1 to get there. That's why sodium was 1 plus, because it had to lose 1 to get there. Magnesium had to lose 2 to get there. So that's why magnesium's 2 plus. What do you think aluminum's going to be? Aluminum's going to have to lose 3 to get there. Okay? And so aluminum, when it's an ion, is going to be 3 plus. Okay? What do you think chloride's going to be? Chloride's just going to be 1 minus, because to get to its closest noble gas, it just has to move 1. Okay? Sulfide, -2, because it has to move 2 spaces. Okay? Phosphide, -3. It has to gain 3 electrons to get there. Potassium is only going to have to lose 1. So potassium is going to be 1 plus. And what we're going to notice is we're going to notice a pattern. The ions in this group are always just going to be +1. Why? Because they only have to lose 1 electron to get to the noble gas number of electrons. These are always going to be +2. Why? Because they'll have to lose 2 electrons to get there. These are going to be +3 because they'll have to move 3 spaces to get there. Then if we look over here, nitrogen's group is always going to be -3 because they got to gain 3 electrons to get there. These are always going to be -2 ions because they have to gain 2 electrons to get there. And the halogens, the halide ions, fluoride, chloride, bromide, iodide, they're going to have to just gain 1 to get that to that stable number of electrons. Okay? So again, the reason why it's called the octet rule is because usually what that means is 8 valence electrons. So atoms gain, lose, or share electrons to get 8 valence electrons, but it's not always 8. And so octet is very much a misnomer. You just want to know that they gain or lose or share electrons to get a more stable number of electrons. And right now, just know a stable number of electrons is 2 or 10 or 18 or 36 or 54 or 86. Why? Because those are the number of electrons as the noble gases, and the noble gases are very stable. So elements want to get to that number of electrons, okay, right now, all right? What's going on in here? A lot of stuff that we're going to get to further down the road, so don't worry about it, okay? So the other thing to maybe notice is when sodium was an ion, we just called it a sodium ion, okay? When magnesium was an ion, we just called it a magnesium ion. But notice when the negative ones were ions, we changed the ending to "ide." So N3 minus, we didn't call nitrogen, we called nitride. O2 minus, we didn't call oxygen, we called oxide. F1 minus, we wouldn't call fluorine, we would call fluoride. So the negative ions, we do change the ending of the name to IDE. Again, you're not technically responsible for that nomenclature yet. Eventually you will be, so you might as well get familiar with it, okay? All right, so that's kind of just a quick lesson on atoms and ions. We'll do a lot of practice with that in class and stuff. But hopefully that clears things up for you, and we will be moving on to 2-2, which is, basically how do we calculate average atomic mass? Okay, so carbon has 3 isotopes: carbon-12, carbon-13, carbon-14. Why is, I'll find it. Right, these are the isotopes of carbon. Why is the average mass 12.01? So that's something to think about. Right? These are the isotopes of oxygen. Why is the average pretty much just 16? Okay? So we'll talk about how we calculate average atomic mass later. Right now, just make sure you understand that there is a difference between the mass that's on the periodic table, average atomic mass, and mass number of a particular atom or ion that you're currently focusing on. Okay? All right. Later.